In the fall of 2003, it unleashed an eruption of energy equal to 200 billion hydrogen bombs, blasting a tidal wave of superheated charged particles at speeds of up to 6 million miles an hour. It was one of the largest solar storms ever recorded. And it was aimed at Earth.
They were some of the fastest, hottest, and strongest storms ever measured.
Assaulting the Earth, the sun's energy forced space station astronauts to take cover in their most sheltered compartments. Lights went out, communication streams were cut, airliners scrambled for safety.
This really was a hurricane of space storms.
Though no major damage was done, these storms were a stark reminder that we live at the constant mercy of the sun. It controls all aspects of our lives, our climate, our food, our bodies.
We actually live inside the sun's atmosphere. We, along with all the other planets, are greatly influenced.
But is its influence changing?
It's actually growing more powerful.
Might we lose its protection from deadly cosmic rays?
At its boundary, where it's protecting us from the intergalactic winds, that boundary is actually shrinking a bit.
Will our technology-dependent society be able to handle another solar superstorm?
Sometimes these effects can be so severe that they're catastrophic.
And when will the next superstorm strike?
Three, two, one, go for drop.
Pegasus is away on the IBEX mission. All Pegasus.
Fall 2008.
Stage 1 ignition.
NASA launches IBEX, the Interstellar Boundary Explorer. Part of its mission is to study the effects the sun has on the furthest reaches of our solar system. IBEX joins the long list of human attempts to explain our star's impact on our solar system, our planet, and our lives.
The sun. The sun provides all of our light and heat. If it weren't for the sun, we wouldn't be alive.
We people are very interested in what goes around us. We like to understand our neighborhood. The sun in the universe is our street, our neighborhood.
The sun. We are actually affected by its moods. In fact, it's like the parent, and all the planets are the children that are affected by its moods.
We need to know how it's going to evolve and how the changes that are always happening in the sun affect us here on Earth.
The sun, if we want to understand the universe and the stars that make up the universe, then it's important to study the one that's closest to us.
We've learned more about the sun in the past 40 or 50 years than in all of recorded history.
This golden age of exploration was kicked off by a unique mission that gave us close-up images of our sun from above our atmosphere.
Skylab, we're reading you loud and clear over the Vanguard for 8 minutes.
In 1973, Skylab became the first manned space station. It sent back images of the sun, clearer than anything taken from Earth.
The Skylab mission was one of the very first laboratories that was dedicated just for the research and study of the sun. In some ways, it's kind of the grandfather of the current missions today.
Right now, a fleet of about 20 space probes scan and study the sun in ways we never imagined, even 30 years ago. By studying the sun from the vantage of space, we can see it in a whole new light, using different light wavelengths, including X-ray and extreme ultraviolet. We can peel back its layers and begin to understand how and why the sun acts the way it does.
The different wavelengths mean different temperatures, and different structures are more visible in different wavelengths than in others.
Our robotic space probes never stop watching the sun. With their help, scientists are working out the big questions about our star, and we already know a lot. The sun is one of over 200 billion stars in our Milky Way galaxy, but it is our closest at 93 million miles away from Earth, almost the same distance as 4,000 trips around the globe. And despite that distance, its light only takes 8 minutes to reach Earth. It is only 4.5 billion years into its nearly 10 to 11 billion year lifespan. And though technically a medium-sized star called a dwarf, It is enormous, 900,000 miles across, and if hollowed out, 1.3 million Earth-sized planets could fit inside. The Sun accounts for 99.8% of the mass in the solar system, and it weighs 300,000 times more than the Earth. It is made up almost entirely of a superheated form of electrified and magnetized gas called plasma. The Sun packs enough gravitational pull to keep the planets from spinning off into space. And as Copernicus first suggested, it rules the center of our solar system with a gravitational iron fist.
Copernicus's model, in which he placed the Sun in the middle of the solar system with all the planets going around it, instead of everything going around the Earth, was a giant paradigm shift. It meant that the Sun is the most important thing in the solar system. It meant that we really should understand the Sun.
Our Sun, like all other stars in the universe, is made from the dust of stars that lived and died over billions of years, going all the way back to the Big Bang.
So our Sun and our solar system is really the debris from many generations of stars.
The Sun we see every day is the solar system's source of power. Deep in the center of our star, its core is superheated to 27 million degrees Fahrenheit and is the engine that drives it all.
Inside the Sun's core, the process of fusion is occurring, and that fusion process is giving off light and particles.
Every second the Sun shines, it releases the same amount of energy as 1 million H-bombs. The Sun's light is made of particles called photons, born in the core, then propelled by convection currents through the radiative and convective zones of the Sun. Eventually, they reach the volatile outer layers of our nearest star.
The Sun's outer parts consist of 3 regions. There's the photosphere, or surface of the Sun, and it's not really a hard surface like that of the Earth. The Sun is gaseous throughout, and the temperature of the photosphere is around 10,000 degrees Fahrenheit.
Above the thin layer of the photosphere is another thin layer called the chromosphere. And the chromosphere is slightly hotter than the photosphere, which is counterintuitive because you would think that as you go away from the source of all the energy and heat, the core, that temperature would drop. But in fact, the temperature rises from the photosphere to the chromosphere. And it gets even hotter as you rise to the third layer of the atmosphere called the corona.
And then beyond the chromosphere is a large, tenuous, extended region, the corona, which is millions of degrees.
The Sun produces a continuous outward flow of energy called the solar wind. Constantly blowing, it carries energy out into the solar system, extending our Sun's reach 9.3 trillion miles, well beyond Pluto.
The space in between the planets and the space in the entire solar system is not an empty void, but it's full of these particles and it's full of these rays of light.
While the solar wind blows away from the Sun, its gravity holds and pulls everything in. Take comets. All comets orbit the Sun and can get pulled directly into the line of fire. Recently, scientists witnessed one of the Sun's most dramatic outbursts, a coronal mass ejection, ripping the tail off a comet.
When it hit the comet, the tail was cut off like you took a knife, and the tail drifted away. And then it took a little more time for the comet to generate more gas and plasma and dust and create a tail. It tells us about how the solar wind moves in the solar system and how it can affect things.
The Sun affects everything it touches, even us. To learn just how much, scientists sometimes rely on a remarkable cosmic coincidence. The lethal output of the Sun has made studying it almost as difficult as understanding it. But scientists can get a good look at our nearest star thanks to a cosmic coincidence. A total eclipse of the Sun.
A total solar eclipse occurs when, from our perspective, the Moon is exactly aligned with the Sun and blocks its photosphere. It's a glorious sight.
The solar eclipse is the most wonderful thing to see. It grows really dark by factors of thousands within seconds. And as it does become so dark, you can look up in the sky, you see the dark shadow coming from one direction, sweeping at you. It's really coming at thousands of miles an hour. So it's very impressive to see.
Humankind has marveled at the mysteries of the eclipse for millennia. Scientists have used it as an opportunity to see the sun's outer atmosphere, the enigmatic corona. One of the hottest regions of the sun, energy from the corona radiates out to the edge of the solar system.
The entire solar system actually sits in this outer corona of the sun. So this atmosphere of the sun is bathing all the planets.
The engineers who built the Solar and Heliospheric Observatory, or SOHO, installed an artificial eclipse into the space probe. Called a coronagraph, it does the same thing as a natural eclipse, blocking out the blinding rays of the sun, so scientists can try and answer an old question.
How does the solar corona get so hot? After all, the everyday surface of the sun, the photosphere, is only around 10,000 or a little more Fahrenheit. And the corona, on the other hand, is millions of degrees hot. If you go away from a stove, you know it gets cooler, but if you go away from the everyday surface of the sun, it gets hotter. And how is that?
It all starts at the sun's core, where every second, nearly 700 million tons of the universe's most common element, hydrogen, are converted into helium through nuclear fusion, giving off the energy that becomes photons, otherwise known as light.
The sun's core is really hot, several tens of millions of degrees. And there the temperatures are so high that protons' hydrogen nuclei can come together, grab each other, fuse, eventually into helium, and in this way release energy.
What happens with these photons, they go through this process, what we call a random walk, where they have to go through the layer of the sun, they get absorbed and then reabsorbed into lots of different photons at lower energy level. So this process of being absorbed and reabsorbed millions of times can take 150,000 years.
Once out of the sun's interior, photons are only 8 minutes away from Earth, but they're leaving behind a world in constant motion. The solar surface boils. Energy rises constantly from below. Coils of plasma and energy, called coronal loops, spring across the sun. While dark regions known as sunspots stretch thousands of miles, and at only 7,000 degrees Fahrenheit, these sunspots are the coolest part of the sun, emitting less light than the surrounding area.
If you were to pluck a sunspot away from the sun and place it in the sky, it would actually be as bright as the full moon.
Sunspots appear on the surface and are easy to see. Their genesis, however, is tied to the sun's deep interior and complex rotation.
The sun doesn't rotate like a solid body. Instead, it rotates more quickly near the equator than near the poles, which leads to sunspots. The equator completes one rotation in 25 days. Mid-latitudes complete one rotation in about 30 days, and near the poles, one rotation is completed in about 35 days.
Called differential rotation, this process makes the sun's interior churn at different speeds, creating intense magnetism in the form of millions of magnetic field lines, which get mixed up as the sun's interior twists up like a rubber band.
This builds up pressure, which makes them buoyant. So they float to the surface, and where they pop through the surface, they create sunspots.
Once on the surface, the now twisted and balled up magnetic field lines block the convection of superhot plasma from rising, making sunspots appear dark.
And when those sunspots start to twist around, you can imagine that you have one sunspot here and one sunspot here, and there's a magnetic field that connects the two. And that magnetic field gets twisted, and eventually, the same sort of thing that happens with a rubber band, it pops. And when the magnetic field pops, it releases energy. And in the case of the sun and solar flares, it releases huge, huge amounts of energy.
The magnetic field lines created by the twisting and churning of sunspots, though invisible, can be seen in the dramatic formations on the surface of the sun, in the form of flares and prominences. It is here that the sun's influence starts, as the breaking of these magnetic field lines drives massive amounts of energy from our nearest star out into the solar system. And it is these magnetic field lines that are behind most theories on why the corona is so much hotter than the surface.
It's pretty clear that it has something to do with the magnetic field that heats the corona. But presumably there are waves along the magnetic field that bring energy from underneath the surface of the sun into the corona.
The solar probe Hinode which means sunrise in Japanese, was launched in 2006. Its mission to study the interaction between magnetic field lines and the corona. Recently, it captured images of one of the waves thought responsible for heating this enigmatic region, Alfvén waves.
Alfvén waves are waves that occur in a plasma, in a bunch of ionized gas, threaded by a magnetic field. And indeed, it's thought that these Alfvén waves might be bringing turbulent energy from inside the sun out to the corona, where that energy heats the corona.
Energetic Alfvén waves form inside the sun and travel up through the surface, making the looping magnetic field lines sway and vibrate.
And so through this vibration or this oscillation, they're having friction with the magnetized plasma surrounding it in the corona. And through this friction, the heating occurs.
It's this heat delivered to the corona that radiates out into space, filling our solar system with the sun's energy. But this energy is not constant. Our sun is an ephemeral body, never the same from one day or 1 year to the next. Like Earth changes with seasons, so does the sun. And when the solar seasons change, anything can happen. Day in and day out, the sun we see appears the same. But like Earth, the sun has seasons, solar minimum and solar maximum. Two distinct personalities that can affect our technology and possibly even our weather. The transition between solar minimums is called the solar cycle, an average 11-year period in which the sun's activity maxes out, then ebbs again.
The primary measure of the solar activity cycle is the number of sunspots visible on the sun.
During solar minimum, the period with the fewest sunspots, solar activity is limited. When sunspots break through the surface during solar max, the sun's power reaches out.
When there are lots of sunspots, there are lots of flares and coronal mass ejections.
Increases in solar activity enhance the connection between sun and Earth. Energy expelled from the sun can create disturbances in the near-Earth environment.
The Earth is embedded in the solar atmosphere, and so what happens on the sun affects the Earth. And that's what we call space weather.
Accurate space weather forecasting is the ultimate goal, but this can be hard. The sun is turbulent, especially during solar maximum, the peak of solar storm activity.
During solar maximum, the magnetic field of the corona becomes very complicated, and you have magnetic field everywhere, all around, even near the poles. You can have coronal mass ejections and flares and solar storms occurring sometimes several times a day.
Solar flares, violent eruptions of energy, usually near sunspots, burst into space. Like a bolt of lightning, quick and powerful, they can happen over a matter of minutes and can give off the same amount of energy as 1 billion megatons of dynamite.
Solar flares are gigantic outbursts of energy from the sun, coming from a very small localized region of the sun's surface. So they're very concentrated ejections of energy that heat the surrounding gas to 10 million degrees.
Solar flare is sort of like a snapping of the whip. It really releases a lot of energy very quickly, accelerating particles almost up to the speed of light.
The particles from the very most energetic solar flares can reach us in something like 15 minutes.
But the solar hurricane of space weather comes from coronal mass ejections. These massive blasts carry billions of tons of superheated gas and plasma into interstellar space.
So coronal mass ejection is where a huge amount of mass and energy is expelled away from the solar surface. So if you can imagine this huge amount of mass and energy traveling away from the sun at these large speeds, sometimes at over 1 million miles an hour.
They throw these like big bubbles of hot gas and magnetic field. It can move off the sun so quickly that it actually creates a shock wave. They're the biggest storms, and they're the important ones for understanding space weather.
Solar probes, like SOHO, have captured the sun expelling massive amounts of energy into space. But scientists are most concerned when they see something called the halo effect, when the cloud of energy appears to surround the coronagraph. That means the sun has aimed its latest blast at us, like in the massive solar storms of 2003.
The fastest coronal mass ejection ever studied in modern times came from these storms.
Shortly after the initial blast from the sun, SOHO was bombarded by charged solar particles, protons and electrons, overwhelming the camera and causing the image to drop out.
What happens is you see a sort of snow on the camera, all sorts of sparkles going by, and that's the particles accelerated by the coronal mass ejection hitting the actual camera on SOHO.
If caught off guard, solar storms can harm astronauts, exposing them to the same amount of radiation in seconds that we receive on Earth in a year.
So if we're going to send astronauts back to the moon and to Mars, it becomes very important to be able to determine when these coronal mass ejections and storms are going to occur. The charged particles embedded in these coronal mass ejections are dangerous. It's a lot of radiation that would hit an astronaut.
Astronauts and satellites aren't the only potential victims of solar storms. The particles blasted towards Earth can interact with our magnetic field, occasionally wreaking havoc.
When this material comes smashing into the Earth's magnetic field, it causes it to ring almost like a bell. And when you have a magnetic field and when that magnetic field moves, physics tells us it's going to create currents. And so electrical currents will be created in the outer atmosphere of the Earth. And these electrical currents can cause all sorts of disturbances.
The currents create problems for satellites orbiting the Earth. They disrupt global positioning systems. They can interfere with communications equipment, causing radio blackouts and knocking out mobile phone systems.
These mass ejections can send so many charged particles toward the Earth that some of them make it through the Earth's magnetic field and even reach power stations here on Earth, causing surges of electrons and power outages and short circuits and things like that.
In extreme situations, solar storms cause excessive radio interference and increased levels of radiation, requiring planes flying near the poles to be rerouted. But as powerful as the storms were in 2003, they're no match for what astronomer Richard Carrington saw in 1859, a super flare.
The super flare of 1859 was incredible because prior to this event, we didn't even know that flares existed. Carrington saw this huge bright flash on the sun with the unaided eye. And in order for him to see that, it had to have been a super huge flare.
There were reports of telegraph lines running without being powered.
We probably won't see another one that intense in our lifetime, although it's hard to say for sure. The sun has thrown us some surprises.
If a similar storm were to strike today, one recent estimate projects 130 million people would lose power, possibly for months.
Most of the electrical infrastructure, the power grids around the world would be knocked out. A lot of the transformers would be overloaded. Having a large portion of the population with no power for many months could cost huge amounts of money. People have estimated that it would be upwards of $2 trillion.
We won't know unless it actually happens, and the more warning we get, the more we can do to reduce the economic impact, which is one of the reasons why we're studying the sun.
Scientists are a step closer to being able to predict these storms since the launch of the Solar Terrestrial Relations Observatory, also known as STEREO. This pair of probes now gives scientists the ability to see the sun in 3D.
So now, when one of these coronal mass ejections travels towards us, we're actually looking at the side view. And so we can see how fast they're traveling, we can see how they're evolving, the structure.
In 2011, the STEREO probes will reach their ideal vantage point, opposite sides of the sun, giving NASA a 360-degree view, allowing them to see what is coming from the far side of the sun before it impacts Earth.
And so for the first time, we're going to have a complete view of the sun all the way around. So this is going to allow us to see everything that's happening on the sun at the same time, and this will lead us again into a better ability to predict these types of storms.
But as dangerous as solar maximum can be for its increase in space weather, the sun's solar cycle counterpart and calmer period, solar minimum, may come with its own dangers.
When there are a low number of sunspots on the sun, the climate here on Earth can actually cool a little bit.
2008 saw the fewest number of sunspots in nearly a century, with a total of 266 sunspot-free days.
In 2008, we were at sunspot minimum, but by now we expected to be climbing out of that sunspot minimum, and we're not. So this could mean that this particular sunspot minimum is more protracted.
Scientists believe that past protracted minimums have had a chilling impact here on Earth.
Now, every once in a while, the sunspot activity cycle seems to just go away or become much diminished. There was such a period around 1650 to the early 1700s.
There were only about 50 sunspots recorded, when normally in the same time frame there are tens of thousands. So it was a really low period of sunspots.
It was called the Maunder minimum. The sun was in a quiet state. And that was associated with lower than normal temperatures here on Earth. Europe experienced sort of a mini ice age during those few decades.
Whether or not this current minimum will be protracted enough to have such a large impact on Earth won't be known for years. But another measure of solar activity, the solar wind, appears to be waning. And that could impact Earth tomorrow. Bathed in the sun's atmosphere, Earth is shielded from deadly cosmic rays. And while the sun's power protects us, it can also harm us. Life on Earth survives this close to its star, thanks in part to its ozone layer. But what would happen if the ozone layer were gone?
If Earth lost much of its ozone layer, ultraviolet radiation from the sun would penetrate through the atmosphere and reach the Earth's surface.
The sun's massive amounts of ultraviolet rays would quickly eliminate most basic elements of the food chain, wiping out plants and then animals.
If we are bathed in huge amounts of ultraviolet light, eventually the life on the Earth would die.
But what could cause such a catastrophic collapse of the ozone layer? Something the sun is supposed to protect us from: a gamma ray burst.
Gamma ray bursts are intense, brief flashes of the most energetic kind of radiation known, gamma rays.
The most powerful events in the universe. In seconds, they give off the same amount of energy that the sun will emit in its entire life. They occur when certain large mass stars die or even collide.
They can be generated from very extreme processes, such as large mass stars collapsing into black holes.
They occur somewhere in the sky roughly once per day, and they come from very, very far away. Most of them are billions of light years away.
But just 8,000 light years away, deep within the Sagittarius constellation, buried in a pinwheel-like formation, looms a potentially ticking time bomb. WR-104. Two stars locked in a cosmic dance, spinning a full rotation once every 8 months. But one of these stars is on the verge of going supernova and emitting a gamma ray burst.
Now, one of these two stars is a very massive star that might someday form a gamma ray burst, and its beam might hit the Earth. If the high-energy beam from a gamma ray burst were pointing directly at the Earth, it could spell real danger.
The radiation from the gamma ray burst would be so intense, very short, on the order of 10, 20 seconds, but this would set up a chain of events which eventually would deplete the Earth of maybe 50 or more % of the ozone layer.
Scientists have speculated that a nearby gamma ray burst caused an ancient extinction on Earth millions of years ago.
At the time, there was only sea life that existed, and even though the sea life deep beneath the sea wouldn't be directly affected by the UV radiation, the plankton and the life on near the surface would die off, and therefore the food chain would be affected.
The threat is heightened even further by something scientists have witnessed over the past few decades: a 20% decrease in the power of the sun's solar winds.
The solar wind is the steady emission of particles from the sun.
They carry the magnetic field that is in the solar corona out into space.
It exists even when there are no coronal mass ejections or solar flares.
The solar wind continues way out beyond the orbit of Pluto and has actually blown a bubble in interstellar space.
Now, that's a bit of a protective bubble because the magnetic fields protect us from charged particles coming from outside.
Normally, solar winds stream off the sun in all directions at speeds of 1 million miles per hour. Pulling the sun's invisible magnetic field along with it, they form the solar system's defense against intergalactic intrusion. the heliosphere.
The heliosphere is the very boundary where the solar wind hits intergalactic space. So it's this shell that's surrounding the sun and the solar system where it protects us from intergalactic winds here on Earth.
Recently, scientists have learned that the heliosphere is shrinking and getting weaker.
The solar wind pressure has been measured to be decreasing over the last 25 years. In fact, the heliosphere, where the solar wind pressure is extending out to, has actually shrunk a bit.
A weaker heliosphere increases the possibility that Earth will be exposed to harm from intergalactic cosmic materials.
So if there's less solar wind, then the heliosphere itself is going to shrink. And that makes it easier for more cosmic rays to enter into the solar system.
Already, the amount of high-energy electrons, a small but telling aspect of cosmic rays around Earth, has jumped in number by 20%.
Looks like the cosmic ray electrons have increased, and you would expect that. If the solar wind has decreased by 20–30% over the last 15 years, the bubble will have gotten smaller, and you expect an increase in galactic cosmic rays.
The good thing for us is that we live on a planet with a thick atmosphere and a magnetic field. So we have two types of shields that protect us.
But that could change when WR104 emits its gamma ray burst, possibly upsetting the balance of Sun and Earth, a balance that may already be in jeopardy because of something the Sun did billions of years ago. Over billions of years, the Sun and the Earth have developed the perfect balance for life to thrive. Sitting in the Goldilocks position of the solar system, not too hot and not too cold. The Sun gives us just enough light, just enough heat, and just enough energy to fuel our planet and our lives.
The Sun drives everything on the Earth. The Sun is the energy source of the Earth. So all of the energy that's given off by the Sun heats up the Earth. This drives weather. On a larger time scale, this drives climate. So basically the Sun is the energy source. It's the battery that drives the whole Earth environment.
Plants harness the Sun's energy through photosynthesis, creating carbohydrates. People and animals consume these carbohydrates, converting them into energy we can use. Even the fossil fuels that power our lives were created by the Sun. But our increased use of fossil fuels seems to be upsetting the balance between the Sun and the Earth.
Since all living material gets its energy initially from the sun is the source of the fossil fuels, whether it's trees, whether it's other things that have been trapped in the rock layer and then squeezed and slowly over millions of years made into the hydrocarbons that we know them as. And we then harvest and use those from underground.
The fossil fuels that we burn today unleash the Sun's energy from millions of years ago, overwhelming the balance struck between our planet and its nearest star.
If we burn all this, we will have changed the atmosphere unrecognizably long before we get to a point when we're actually running out of the resource itself.
Already, we have seen the effects of too much solar energy in the rise of global temperatures. The release of millions of tons of ancient solar energy stored in fossil fuels has amplified the necessary and natural process called the greenhouse effect.
Many people think that the greenhouse effect is a bad thing. Well, in fact, it's not. It keeps the Earth warm. Without the greenhouse effect, Earth's oceans would be frozen solid. What is bad is too much of a greenhouse effect. If there's too much carbon dioxide and water vapor and methane in the Earth's atmosphere, then those gases trap too much of the Sun's radiation, elevating Earth's average temperature, leading to global warming. Now that can cause a melting of the polar caps and a rise in the ocean levels, leading to just a calamity on Earth if it happens too quickly.
Not only will our atmosphere continue to trap more heat, it could start to decay. Continued use of fossilized solar energy will allow in undesirable amounts of radiation from our Sun. Right now, our ozone layer prevents the majority of the Sun's ultraviolet radiation from reaching Earth, while allowing just enough sunlight to give us what we need to survive.
Sunlight interacting with our skin produces vitamin D, which is a very useful vitamin.
Vitamin D can protect us from a number of diseases, including the bone disorder osteoporosis and heart disease. But here too, a balance has been struck. Too much sun can alter our DNA, causing skin cancer. Maintaining the equilibrium between sun and earth that allows life to thrive will require using less of the sun's ancient energy and more of the energy it delivers on a daily basis. After all, the sun's energy output is estimated to be 386 megawatts. Meaning in 15 minutes, our star radiates as much energy as all life on Earth consumes in 1 year. Tapping this power source has been the goal of scientists for decades.
For sheer size, a solar satellite would be unprecedented. A structure 35 to 40 square miles covered with solar cells, able to capture the sun's energy 24 hours a day and beam it to Earth.
NASA has yet to achieve a goal on that scale, but their work with solar technologies in space has advanced technology here on Earth.
History of solar cells is essentially a technology that came back down to Earth from space. When we first started to work on the Apollo and Mercury and Gemini programs, we needed power plants in space. Solar cells were a natural way to do that.
Currently, we have two ways of directly harnessing the sun's energy. Solar thermal, which converts the sun's energy into heat by concentrating it enough to drive turbines, and solar panels, which use silicon-based technology to directly convert the energy from above into electricity. We can indirectly tap into the sun's power through wind turbines, capturing the energy produced by the weather the sun helps create. These technologies are constantly being improved. But some of the most interesting new science is coming from a very old process, photosynthesis.
There's some really exciting opportunities as we move from the world of semiconductor solar cells to organic ones.
Attempting to mimic Mother Nature, scientists have been able to create electricity from something found at the farmer's market, spinach.
There's organic molecules in spinach, in all green plants, but spinach happens to have a very convenient one, where you can harvest that peptide, that molecule.
Researchers were then able to put that peptide into a kind of solar sandwich, placing it between two electrically conductive materials.
And when it's exposed to sunlight, it will circulate electrons, which is current, which is electricity. So these organic molecules can actually become little solar cells.
In order to maintain the balance between Earth and our nearest star, it's become clear we must focus on finding ways to fuel our lives with the energy the sun supplies today. After all, the promise of solar energy is that for as long as the sun shines, its power can be ours. But what will happen when its power becomes too plentiful? The elements that make up the sun, the earth, and even humankind all come from one place, stardust, the remains of stars that lived billions of years ago. And just as those stars died, so too will our sun.
In about 5 billion years, the sun will pretty rapidly become much more powerful, much brighter, and much bigger.
The sun will reach a stage where it has burned through all of its hydrogen. And once that happens, it will start to burn through all of its helium.
The sun will start to expand as it reaches a stage called a red giant. As it expands, it will start to expand into much larger size and fill the inner solar system.
The orbits of the planets themselves will actually expand outward as well, because it's not as massive.
During that stage, some instabilities, which I call cosmic burps, will cause the sun's outer atmosphere to be gently ejected.
The outer layers of the red giant will just keep drifting off at some slow rate.
The hot inner layers of the sun will ionize that cloud of gas surrounding it and cause it to glow. So our sun will be surrounded by these glowing clouds of gas.
They will form what's called a planetary nebulae. They're beautiful shapes. Some are just purely round, but some have been distorted into other shapes. They've come off non-symmetrically from the star underneath.
What'll remain is the contracting core of our sun. And it won't produce any new energy through nuclear reactions, because all the nuclear reactions will have stopped. So it'll continue contracting and slowly fading with time.
It's very similar to the process that creates, say, supernova, but our sun is not big enough, doesn't have enough stuff to actually create a supernova. So its final stage will be this object we call a white dwarf star.
What remains is this little, relatively small white dwarf star, and it is a very quiet, what we call happily retired star.
It'll be about the size of the Earth, it won't get any smaller, and it'll sit around as this very highly compressed rock forever. It'll just liberate its energy, growing ever colder and dimmer with time, until finally it just fades from view.
The death of the sun will have catastrophic effects on the solar system. If the massive expansion doesn't swallow the nearby planets, it will likely change their orbits and superheat them, including Earth.
Earth's surface will be fried to a crisp.
The Earth is probably going to get baked one way or the other.
I mean, imagine the sun being 100 or 200 times brighter than it is right now. Imagine how much the Earth would be heated. It would not be a pleasant place to be.
It actually may get baked before the sun completely dies, because the sun will get hotter even before it becomes a red giant and gets as large as the orbit of the Earth. It'll get warmer, and at some point the Earth will get hot enough so that water will boil.
So the oceans will evaporate away, and all of life as we know it will cease to exist.
If there's anything left of the Earth, the sun will shrink down to a white dwarf, and the Earth will, instead of heating, freeze.
This will not be a pleasant place to live.
But that's billions and billions of years from now. We've only had rockets in space, satellites, for 50 years or so. Now we're talking billions. So clearly we'll be able to travel around the solar system at the very least, to go to places that will be at the temperature that the Earth is now, and we'll be able, by that time, to go to more distant solar systems. So I don't spend a lot of time worrying about what's going to happen to the sun in 5 billion years.
The sun gave us our life, and it will eventually take it away. And though the Earth will die, it and everything on it will, in some part, live on. The stardust that gave Earth and all of its inhabitants life will one day become the stardust that gives rise to a new generation of planets, stars, and life.
Planets so weird, even science fiction could not foresee them. For the first time ever, scientists are discovering alien worlds beyond our solar system. Places where ice is hot and rain is made of iron. They are uncharted, unearthly, and unpredictable. And somewhere, hidden among these strange new worlds, scientists seek the greatest discoveries of all. Planets like ours, alien Earths.
35 seconds. Storage tank press closed.
March 6, 2009.
22 seconds. Later, GN2 pressure go.
This Delta II rocket is going through its final pre-flight check.
7.3. Drop 1.
Engine start, 1, 0, and liftoff.
It is the start of an extraordinarily ambitious mission. The Kepler Space Observatory is hunting for planets like Earth within a region of 100,000 stars. It is the culmination of a journey that began more than a decade ago with one of the most profound scientific discoveries ever made. In 1995. Swiss astronomer Michel Mayor and his team make a routine observation of stars in the constellation Pegasus, located 50 light-years away. But the instruments show something strange. One star is violently lurching and wobbling.
What we discovered, it's one of these stars have a velocity changing with time.
What is powerful enough to disturb a star the size of our sun? Mayor offers a radical answer. a planet. But no one has ever seen a planet around another sun-like star.
Problem in detecting planets around other stars is that as a planet orbits a nearby star, that planet gets lost because of its feeble light in the glare of the very bright star.
In spite of the odds, Mayor relies on his data and is convinced the wobbles are caused by the gravitational pull of an orbiting planet.
When I read this claim from Michel Mayor, I was very skeptical. There had been many false claims of the first planet ever discovered around another star, and I thought to myself, oh boy, here we go again. So I decided to observe the star on 4 consecutive nights. And stunningly, the star was shown to wobble exactly as Michel Mayor had said.
Michel Mayor and his teammate Didier Queloz announced their discovery. It rocks the scientific community.
They had found for the first time reproducible, confirmable evidence of the existence of a planet around a sun-like star.
Officially called 51 Pegasi b, the planet is nicknamed Bellerophon, in honor of the Greek hero who tamed the winged horse, Pegasus. It is a planet that breaks all the rules. Bellerophon roasts in the blazing starlight at temperatures of roughly 1,800 degrees Fahrenheit. It is nearly 150 times more massive than Earth and is a gas giant like Jupiter.
A gas giant is a planet made mostly of hydrogen and helium. Only the outer layers are gas, but inside, hydrogen and helium is compressed to huge, huge, huge pressures. It doesn't resemble a gas at all.
Unlike anything found in our solar system, this is an entirely new class of planet, what scientists call a hot Jupiter.
If you go to Hawaii and see the lava flow there, that's how hot a hot Jupiter is. It's very, very hot.
The Earth is a comfortable 93 million miles away from the Sun.
These hot Jupiters are roughly 100 times closer, and so the amount of sunlight that they get is 10,000 times larger.
If this represents a star, and this a hot Jupiter is 3 to 4 stellar diameters away from the star. So that would be 1, 2, 3. This is how close a hot Jupiter would be to its star. Hot Jupiters are tidally locked. They present the same face to the star at all times, just like the moon does to Earth.
It's going to be permanent daylight on one side and permanent nighttime on the back. If I were stuck on a hot Jupiter, I'd want to be on the back side and hope that some of the heat from the front side facing the star would make its way around the back.
The variations in temperature make Bellerophon's atmosphere extremely windy. The wind howls at thousands of miles per hour, far beyond anything we could ever withstand. The heat blast guarantees water vapor cannot exist. But that doesn't mean there is no rain.
It's far too hot for water liquid clouds to form here. But instead, these clouds would be made out of iron.
Iron vapor can exist at temperatures much higher than water. And because of that, things could get a little messy.
You better have an umbrella that's pretty sturdy, because the iron is going to start coating your umbrella very rapidly and making it extremely heavy and just crush that umbrella.
The sky overhead is filled with dancing curtains of color. Charged particles from the nearby star make auroras far more extreme than the northern lights on Earth. There is something even more unique about this newly discovered world. Bellerophon orbits its sun in a blistering 4.2 days.
No self-respecting planet goes around a star in 4.2 days. None of the planets in our solar system take such a short amount of time.
For scientists, the tiny orbit challenges long-held notions of how planets form.
The fact that the planet was orbiting every 4 days was a total puzzle until one night in the middle of the night I woke up and said, well, this must be proof that planets migrate inwards. They don't stay put where they are.
The key to the puzzle is found in how planets are made.
Planets are a byproduct of star formation. When stars form, they have a disk of dust and debris around them, and out of that debris, planets form.
Much of what we know comes from Hubble's Space Telescope, as it aims at regions like the Eagle Nebula. This interstellar cloud is studded with collapsing disks of dust and gas. A giant clump grows in the center of each disk. Temperatures reach a searing 18 million degrees. The same nuclear fusion that powers our sun is unleashed. The star is born. Radiation from the star generates a stellar wind that sweeps away leftover dust and debris. Some of the dust survives and remains in orbit around the newborn star. Over millions of years, the dust sticks together, forming knots that grow into asteroids, and the asteroids grow into planets. These planets migrate through the disk until they find a stable orbit. This is why Bellerophon is so close to its parent star. But one newly discovered world has found its stable orbit in a place no planet should ever go. 2001. Hubble Space Telescope is directed to an obscure star some 150 light-years away from Earth, in the constellation of Pegasus. This is the same region where Bellerophon was found 6 years earlier. Hubble is tracking another hot Jupiter, discovered by astronomer Jeff Marcy. But this one is different from Bellerophon.
You've probably heard of the planet HD 209458b. It's a terrible name.
A terrible name for a terrible place. HD 209458b has been dubbed by some as Osiris, after the Egyptian god of the dead. Osiris is over 200 times more massive than Earth. It has migrated perilously close to its sun, at a mere 4 million miles from the blazing solar surface. Osiris broils in a planetary hell. The average daily temperature on Osiris is over 2,000 degrees. Forget global warming. This is global frying, and it causes Osiris to lose an estimated 550,000 tons of air every second.
There's a leak of gas, a steady stream of hydrogen and helium, and that's making a big, huge cloud all around the planet.
Its atmosphere is bleeding into space. Scientists speculate that a colossal trail of gas spirals behind the planet for thousands of miles. Osiris presents an unprecedented opportunity for astronomers. Using Hubble, they analyzed the alien planet's bloated atmosphere.
This is the absolutely first time where we could tell what is the composition of the atmosphere of an extrasolar planet.
Surprisingly, Hubble detects many of the basic chemicals needed for life. Sodium, carbon, hydrogen, and oxygen. But Osiris is far too hot for life as we know it.
There may be other forms of life, however, that thrive on higher temperatures.
But there's no solid surface as we know it on a hot Jupiter. So this life would have to be just tiny little microbes floating around on aerosols. And on our own Earth, we have life that floats around in our atmosphere. But that life didn't start there. So life almost certainly would not exist on hot Jupiters.
Astronomers have discovered many hot Jupiters since Bellerophon was found in 1995. But conditions on these worlds rule them out as places where the drama of life can unfold. One of these gas giants is a planet that teases the rules of evolution. Astronomer Jeff Marcy discovers something shocking about a planet orbiting a star called 16 Cygnus b, located some 70 light-years away in the constellation of Cygnus, the Swan.
The planet was clearly in an elongated orbit, bringing the planet close to and then far from the host star. And this, of course, defied our expectations based on our own solar system, where all of the planets go around our sun in nearly circular orbits like phonograph grooves in a record.
Like a giant yo-yo in space, the gas giant swings back and forth across its solar system. That is like the Earth swooping 25 million miles closer to the sun, then slinging past Mars, all the way out towards Jupiter every year. And like all of the gas giants in our solar system, this yo-yo planet might have an entourage of moons. Marcy speculates that one of these moons could be similar to Earth.
And here's where the interesting story begins. Imagine a rocky moon with lakes, oceans, maybe streams and waterfalls on the surface. The moon orbiting its planet, the two of them orbiting the host star.
Unlike the airless moon that circles the Earth, this moon is a world with extreme seasons. On Earth, the seasons are caused by the tilt of our planet. Here, they are caused by the elongated orbit.
These poor planets that are in these elongated elliptical orbits suffer terrible changes in their climate throughout a year.
As they make their closest approach, the yo-yo planet and its moon are blowtorched by the star. Summer begins. The atmosphere on the Earth-like moon is savaged with raging storms. Category 5 hurricanes on Earth are tiny eddies compared to the monster vortexes that form here. The clouds thicken as the water evaporates.
Temperatures rise dramatically. Any water or gases would heat up, and indeed the oceans would boil into steam, so you'd end up with a big steam bath.
During the peak of the summer, the entire moon is smothered in 800-degree temperatures. This is the closest approach to the star. During its 26-month orbit, the summer season is barely 2 months long. But what a season! The planet and its moon swing away from the furnace of the star. Temperatures fall to ranges we would find temperate and comfortable. With the coming of fall, the rains return to the parched and roasted moon. Dry ocean basins are replenished, and the seas rise to form new shorelines. Tranquility prevails as the yo-yo planet and its moon slip into the deep freeze of winter. Now, over 200 million miles from the star, the daytime sky is dark. Temperatures hover around 260 degrees below. Winters are long, lasting 17 months. With the coming of spring, the sun looms large in the skies over this hapless moon as the ice cracks and melts violently. Huge icebergs calve into a stormy and fast-rising ocean. For 2 preciously short periods, during the spring thaw and the autumn rains, the climate on this Earth-like moon is balmy and comfortable. At a distance of 93 million miles from the star, roughly the same distance as Earth from the Sun, the elliptical orbit of this planet and its moon crosses an area around the star some scientists call the Goldilocks zone. The conditions here are just right for life.
If you're too close to the star, then it's too hot. If you're too far away, then it's going to be too cold and everything's going to be icy. But then if you're right in the middle, it's just right.
Every star has a Goldilocks zone. Where that zone is depends on the size and temperature of the star. In our solar system, Venus marks the inner boundary and Mars the outer boundary. Earth and its abundance of life is right in the middle. The yo-yo planet passes through the Goldilocks zone twice a year. For 3.5 months during the spring as it races inbound, and again in the fall for 3.5 months as it hurtles back into the colder reaches of space. Could life survive the conditions outside the Goldilocks zone?
There could be life forms that are smart enough to hibernate, as do animals on the Earth during the winter season. If this sounds fantastic, I offer you the tidal zones on the Earth. On the tidal zones, life proliferates, of course, near the seashore. So despite tides, the water coming in, covering many of the life forms, the water going out at low tide, and yet those species survive perfectly well.
The strange cycle of the yo-yo planet's orbit creates fleeting conditions suitable for life, but also for death. Some alien planets are even more bizarre. Imagine a world that has no star to orbit. Scientists speculate that our galaxy is teeming with rogue planets, adrift in the murky lanes of interstellar space. These are orphaned worlds, planets that are booted from their solar systems by the chaos of planetary migration. Astronomers call such worlds planemos.
Planemos are planets without a star. They're just drifting through the galaxy indefinitely.
What massive force would it take to kick a planet out of the solar system?
When a young star forms with a contingent of planets around it, many of those planets gravitationally interact with each other. They yank on each other, slingshot each other, so that one of them is ejected from the planetary system, voted off the island, if you will.
If you were, unfortunately, a resident on a planet that was kicked out by a collision or a near collision with another large object, you'd probably rapidly move out of the habitable zone.
There are hundreds of billions of these lost, wayward, poor, wandering planets out in our Milky Way galaxy with no parent star to warm them up.
Cold, dark, quiet. Because planemos have no sun, they are worlds without days or years. They keep vigil through an eternal night. Planemos are solitary wanderers, sentinels of the galaxy. Just because it's out there drifting in space doesn't mean a planemo is dead.
If the planemo is a rocky world, it could well have life on it.
A small rocky planemo without an atmosphere will slumber in extreme cold, far colder than the coldest winter day on our own South Pole. But a planemo large enough to retain an atmosphere traps the heat generated when the planet was first formed. It is the ultimate greenhouse effect. The heat and energy comes from the molten core deep inside the lonely planet. If the planemo is a gas giant like Jupiter, it may have a system of moons. The gravitational pull between the planemo and its moons creates friction, causing the interior of the moons to stay warm.
These moons could also have life on them, in the same way that Jupiter's moon Io has volcanoes and has a lot of heat energy being generated by interactions with Jupiter and the other moons.
If anything lives here, it will be single cells, like common bacteria found on Earth. Not complex life forms. Without a sun to provide photosynthesis, these tiny organisms derive their energy from the chemistry in the soil of the planemo, or its moon. On Earth, there are similar conditions. Colonies of bacteria are found deep within mine shafts in South Africa. They have no access to oxygen nor light and survive entirely on the chemicals they make from the surrounding dirt. Their metabolisms are extremely slow, and they reproduce only once every 1,000 years. If life dwells on a sunless planemo, it could be organisms like them, marooned when their planet was young. While planemos slumber undisturbed, there are worse places to be in the universe. Like in the company of this lethal pulsar, some 980 light years from Earth, in the constellation of Virgo. From afar, a pulsar looks like a blinking light, but up close, pulsars machine gun their surroundings with deadly radiation. They are no place for planets. Yet something interferes with the precision of this pulsar. One explanation is that the anomaly is caused by a planet. But many astronomers are skeptical that planets orbiting a pulsar can exist.
The reason that's a problem is because pulsars are formed in these incredible explosions.
When a red giant star explodes, a titanic fireball known as a supernova unleashes as much energy in 1 minute as our sun generates in its lifetime.
When a star goes supernova, the shockwave is so immense it's hard to imagine any planet surviving that.
When the cosmic dust clears, all that remains is the crushed core of the red giant, pulsing in the heart of an expanding debris field. Matter blasted from the colossal explosion falls back to the pulsar and forms a disk. Within this chaos, a new world arises, born of fire and destruction, a planetary zombie raised from the carcass of the former red giant star.
It's amazing that planets could form in that environment.
A planet orbiting a pulsar will give you the feeling of being in a disco bar with a very strong strobe light, which is the pulsar.
Radiation from this stellar beast breaks down the organic molecules needed for life.
The pulsar has these very strong magnetic fields that are being spun around as the star is rotating quickly, and it's picking up any material, electrons, protons, and speeding them up and slinging them out at high speed. So it's like a solar wind with a vengeance.
I can't imagine that there would be much of an opportunity for even simple life, microbial life, to emerge and to flourish on a planet around a pulsar. Largely because if you were in the pulse, you'd be severely energized, and if you were not in the pulse, you would be completely devoid of energy.
The discovery of pulsar planets shows how new worlds can form in the wake of a star's destruction. No matter where a planet arises, the process of its birth is fraught with danger. Sometimes, the violence is so great, the end of the world comes before the beginning. 2007. Astronomers using the giant Gemini North telescope make a strange discovery in the Pleiades cluster some 400 light-years from Earth. A star known only by its catalog number, HD 23514, is surrounded by a giant donut-shaped cloud of dust and gas. The star in the middle of the donut shape is about 100 million years old. A cosmic toddler in astronomical terms. Our sun is 45 times older. The conditions are perfect for planets to form. But spectral analysis finds something strange. The dust is utterly pulverized. Typically, a newborn star is surrounded by fledgling planets.
Planets form around the young star in a protoplanetary disk of gas and dust. And then these planets go on their merry way orbiting the star, not realizing that they're in an orbit that's too close to another planet.
Millions of years ago, two primordial planets orbiting HD 23514 are spinning toward doom. As the two worlds close in, tidal forces torque each planet from spheres to egg shapes. Nothing remains. The two worlds are annihilated, creating the dust and debris seen around star HD 23514. 4 billion years ago, a similar apocalypse came to Earth. A Mars-sized planet forms in roughly the same orbit as the newborn Earth. Like the planets at HD 23514, Earth and this Mars-sized body are barreling toward each other.
If you happen to be unlucky enough to be standing on a growing planet when the process was still becoming the Earth, you might wake up one morning and notice that the sky was getting darker and darker as a Mars-sized body was coming at you within a period of less than an hour.
And when it hits, the shock wave is felt all over the planet, scouring the surface of the Earth. The collision obliterates one side of the planet. Molten rock sprays out into space. The entire globe is peppered by meteors and noxious vapor.
It would actually make hell look like a Bahamas vacation.
The debris field from the collision coalesces and forms our moon. It is a new beginning for our planet.
Collisions are part of the birth process for planetary systems. Building up a terrestrial planet is probably all about colliding pieces of rock together.
And all across the galaxy, colliding pieces of rock are forming terrestrial worlds that defy the imagination.
There is a new planet out there, a planet we were not aware of existing before.
It is not just one planet. It is a new type of planet. Earth on steroids.
I like to call them super-Earths. They're just like the Earth, except bigger, up to about 10 times the mass of the Earth. One family that the super-Earths resemble just like our own Earth. Continents, oceans. Some of them may be very dry, like Mars. And then another family that we call water worlds or ocean planets that are completely covered with water.
Welcome to Gliese 581c.
This planet was found by Michel Mayor, and it orbits with 2 other planets around a very small star.
It's only 20 light years away in the constellation of Libra and is one of the smallest terrestrial planets found beyond our solar system. That doesn't mean Gliese 581c is small. It's still a super-Earth with 5 times the mass of our home planet. But it's the possibility of liquid water that excites scientists.
An ocean planet feels like being in the middle of the Pacific Ocean, with no land in sight, just water, puffy white clouds, and blue sky above you. The winds on the ocean world are going to be similar to that of the Earth, so it will be a very good place to sail.
The weather's absolutely perfect. Every day you get a clear blue sky and the sun just stays in the same place. Now how's that for weather prediction?
No land anywhere. Even miles beneath the surface.
This water layer would extend very far down, at least a quarter of the way down in the planet.
But as we dive deeper into the sea, the pressure builds. At 35,000 feet below the surface, we pass the point where the deepest oceans on Earth bottom out. We pass the 100,000-foot mark. The pressure is so great, water itself begins to take on surprising new forms. At a depth of 10 times the greatest ocean depth on Earth, we reach the bottom.
When you have a large amount of water, then at the bottom of an ocean, you will form very high pressure in excess of 1 million atmospheres. And that pressure will compress the liquid water, that is the ocean, into a state which we call ice 7.
No, it's not like ice in your refrigerator. The molecules of water that are in the ice in your refrigerator are kind of all jumbled up. But if you form ice under very high pressure, then the water molecules can become ordered, they can become aligned. I can show you a crystal that is a very good analog to ice 7. This is halite, also known commonly as rock salt.
Ice 7 may exist within our own solar system. Europa, a moon of Jupiter, could possibly have a mantle of liquid water surrounded by a thick, icy crust. The pressure from the crust is so great that Ice 7 might exist deep within these uncharted seas. If we scale up and thaw out Europa, it could be a water world similar to Gliese 581c.
One could imagine that life could emerge on a water world. After all, water is essential to life on Earth.
Everywhere on Earth where there is water, there is life. You cannot find a sterile drop of water on Earth unless you put it in the microwave yourself.
On this water world, there could be bacteria or any kind of life in the ocean itself.
But not all of the super-Earths are water worlds teeming with life.
When we talk about super-Earths, we talked about two major families of mostly rocky with some water and mostly water with an endless ocean. But one has to add to those a third family of probably very rare super-Earths and Earth-like planets, which are called carbon planets.
A carbon planet is unlike anything we've ever seen anywhere. A place with an alien chemistry, but loaded with very earthly treasures. Throughout our galaxy, there are planets barren and poor and inhospitable. But science is on the trail of a new type of planet, an entire world of treasure.
In our own solar system, in our sun and in all the stars nearby, there's always more oxygen than carbon. But if we think of a place in the universe where there's more carbon than oxygen, then planet formation is very different.
Spectral analysis shows carbon to be far more plentiful, 26,000 light years away near the center of our galaxy. Planets that form here may contain a rich abundance of carbon. The morning sky on a carbon world would be anything but crystal clear and blue.
I'm picturing a yellow haze with black clouds of soot. And as you descended farther down in the atmosphere, I could imagine lakes that were made out of compounds like methane or gasoline. I'm picturing these bubbling, foul-smelling pits of black ooze, like an oil well.
With little or no water in the atmosphere, the air is made of carbon compounds.
Methane, butane, pentane, benzene, all these different kinds of carbon compounds that separate out when you refine gasoline. One day it might be raining benzene. The next day it might be raining butane.
Alien as carbon planets might seem, the air quality could be familiar to some.
The air in a very benzene-rich planet will resemble that of LA. A lot of small particles that unfortunately we are quite used to from the exhaust of cars.
Despite the pollution, carbon planets could come with a sparkling upside.
You might see diamond because the planet may have substantial quantities of pure carbon that it's formed out of. And pure carbon, when you compress it, tends to form into diamond.
The secrets of exotic planets like these are waiting to be discovered all across the galaxy. But astronomers won't be satisfied until they find the Holy Grail. A planet like our own, one that sustains life, the next Earth.
People always ask me, do I think we're going to find another planet like Earth? And I answer, absolutely.
Every star probably has planets roughly the same size as our Earth.
We think that essentially every star has several Earth mass or super Earth mass planets. So if you have, say, 200 billion stars in the galaxy, that may mean there are 400 billion Earths in the galaxy or more.
400 billion Earths. The Kepler Space Observatory is the first instrument capable of finding one of these planets.
Kepler is looking at the constellation Cygnus in the night sky at 100,000 stars, taking picture after picture after picture, minute after minute. And the goal of Kepler is simple: to look for stars among the 100,000 that dim.
When a star dims slightly, it means a planet passes in front, blocking some of the light. How long the star dims and how much light gets blocked will tell scientists about the size of the planet and the distance from its sun.
A good analogy for this is looking for the dip in the light that you would see from a searchlight if a small moth flew across the searchlight. And so it's a really tiny dip in the light as the planet transits.
It is a very powerful technique because it allows you to discover planets that are even smaller than the size of the Earth around stars similar to the Sun.
It is a technique that is changing the course of science.
We think we may be able to find a planet that is habitable in the next few years.
Scientists estimate the Kepler mission will find a minimum of 50 alien Earths.
One of the big questions that anybody looking for life beyond the Earth is facing today is, what if we don't recognize life even though we discover it?
Conditions on an alien Earth may cause life to evolve differently.
My hope is that we'll see some sign that will make our hairs stand up on the back of our necks.
Whatever that sign is, it will be the first chapter on the greatest scientific story ever told.